All right, guys. Excuse me. So this is like part 2 of like the weird things that we didn't really ask you to do in class, but like we can adapt it given what we know so far about how to calculate things on shapes. And so here we have part A. We want to perform a calculation that confirms the diagonals of the rhombus ABCD are perpendicular. Well, let's first draw on the diagonals. And per the last page, the diagonals here just go across the shape. And so here we have the red diagonal, and I guess we can draw in this one too. Okay, now we want to confirm that the diagonals are perpendicular. So even though we are dealing with something weird like diagonals, perpendicular is not weird to us or shouldn't be weird to us whatsoever. Perpendicular, the thought process should be twofold. If we're going to calculate perpendicular, that means we're calculating slopes, and moreover, the slopes have to be opposite reciprocals. Okay, so if the slopes are opposite, so we're going to calculate the slopes and we're going to find their opposite reciprocals. That should confirm that we either do have a perpendicular intersection or we don't. Now, to find slopes, we have a couple different methods. One was using kind of rise, run, but drawing in the triangle first. And so I'll do that for the red one because honestly, that's pretty easy to do. So we have a drop of 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we have a run of 10. And so if we want to find the slope of the diagonal AC, change in y over change in x. So the change in y is -2, and we have a run of 10, simplifying to -1/5. And we usually do want to simplify all the way. All right, now we could do that for this one, but it looks like some of the numbers are in fractional form. And so I guess we could change, we could either have the choice to change these fractions into decimals, or we could just go ahead and use, we could use the slope formula. And I think I'll choose to use the slope formula here. So let's see, slope of BD. Although you could draw triangles again and then count that out. This for me is just as easy. We take y2 minus y1 over x2 minus x1. Okay, so we look at the change in the y's, y2 minus y1. So we have we have 4, subtract off -2. We should look at the change in the x over the same interval. So we got to go 3/5 and then subtract off -3/5. Now 3/5 as a decimal is just going to be 0.6, 246. And so this is just going to be 0.6 subtract the -0.6. Okay, so a little more complicated, but nothing outside what we can handle. 4 plus a -2. Okay, 0.6 plus 0.6 is going to be 1.2. Okay, and again, we have to deal with this as a comparative number. Since it's already in decimal form, I'll go ahead and make this a decimal too. So 6 divided by 1.2 is going to be 5. Okay. Well, now let's compare them. So we have a slope of 5, which is the same as 5 over 1, and we have a slope of 1/5. So those by rule are opposite reciprocals. Okay, so we know that AC is going to be perpendicular to BD. Okay. Now again, this is a weird application. I know that. We haven't done a problem precisely like this in class, but it's not outside what we can do because the key phrase here is perpendicular. And so no matter what the context, if we're looking for perpendicularity, we're always looking for slope, whether that be of the side lengths or the diagonals. Okay, and if we're going to be show perpendicular, they have to be opposite reciprocals. So here we have a question where we're going to have to perform a calculation that confirms the the diagonals of the rhombus ABCD bisect one another. So you know what we're going to do first. Let's draw on those diagonals. AC, BD. Okay, and we want to know. We have to perform a calculation to show that they bisect one another. Okay, and again, the operative phrase here, the thing to pay attention to is bisect. And so in other words, we want to know they cut each other in half. And so what we really want to find are the midpoints. And we want to see if they're the same. Midpoints, P-O-I-N-T-S. There we go. Man, my pen's really cutting out here, all right? So midpoints means we're using midpoint formula. Okay, so AC, so the midpoint is going to be x2 plus x1 over 2, y2 plus y1 over 2. All right, so the x's go from -5 to 5. So -5 plus 5 over 2. At the same time, the y's go from 2 to 0. So that'll be 2 plus 0 over 2. -5 plus 5 is 0. 0 over 2 is still 0. 2 plus 0 is 2. Over 2 is going to be 1. And so we know the red midpoint is going to be at 0, 1. Okay, so we'll repeat that for BD. Okay, so alrighty, so we add the x's together. So we have -3/5 plus 3/5. Then divide that result by 2. And so we start at the bottom, so -2 plus 4 over 2. Well, -3/5 plus 3/5, it's like any negative version of a number times it, or plus itself. That's going to be 0. 0 divided by 2 is 0. 2 plus 4 is 2. 2 divided by 2 is 1. And so we also end up at 1. There we go. That's a little easier to read, I think. All right, so what does confirm for us? Well, it confirms that since the middle point of both of these diagonals are in the same location, then these do indeed bisect one another. And again, that's a very arbitrary problem, but the thing that you should focus on is that if we're looking for diagonals being bisected, we're using midpoint. And so the bigger idea behind these problems is what formula do you use to do the thing that it's asking, right? And so if you have to find distances, congruencies, you use the distance formula or Pythagorean theorem. If you have to find where things, like if they bisect one another, you're going to use midpoint. If you're going to find perpendicularity, you use slope. That is actually the more important takeaway out of these problems than the problems themselves. Okay, so we have one more group of 2 of weirdo problems, and then we move on, I think, to areas and perimeters.